Hello and welcome to this homework help video where we're going to talk about a couple of problems involving the basic fluid or physics of fluids. And we're just going to be talking about fluids at rest here, and we're going to talk about buoyancy and about something called Pascal's Principle, which is about the way that force gets delivered through a fluid, which makes a mechanical system, like a lever essentially. So let's go ahead and take a look at the first problem. All right. So this first one here, I'm going to go ahead and number these. So we'll call this one number 2, or number 1 rather, and we'll call this one down here with the pistons number 2. Okay. So in problem 1, we are told that there is a rectangular barge. It's floating in water, and let's go ahead and choose some different values for the numbers here. So I'm going to make my barge have a size of, say, 5 meters across. So let's have 5 meters on one side, and then this rectangular barge will be 4 meters on the other side. Okay, so kind of close to a square, but not quite. And let's go ahead and put a little sketch in showing our barge in water right over here. All right, so here is some water. And the idea then is that we want to show the dimensions of the barge. So I'm going to kind of draw it in a 3D perspective so we can see that the barge has a particular length and width like so. All right. And we'll go ahead and move our water over a bit. Let's do this so it's not overlapping. Okay. All right. And so then our dimensions are going to go ahead and be 5 meters on this side and then 4 on the other. Okay. So we're then told that a particular object, which we'll just put here as a shaded in black square. So we'll just have this right here, has a mass of, let's go ahead and make that, how about, not too heavy, but let's make it 290 kilograms. All right, although it's a big enough barge, that's probably fine, but we could have done more. Regardless, this is going to be our mass, and I'll go ahead and call that M, right? So this is going to be a little placeholder so that I can label it in a figure as M. Okay, so essentially there's a wooden barge. It's like a big plank of wood, and it's floating, right? It's certainly buoyant enough to float, the wood being less dense than water. And we're going to put something on top of it, and the barge will presumably remain floating. We're not concerned about whether or not it takes on water. What we are concerned about is that what's happening is that the barge is going to sink a little bit into the water because of the extra mass put on it. And the whole principle here is going to come down to that the mass that's being placed on the barge will displace a certain amount of water. Okay, so let's then think about what's going on. So we have a gravitational force acting on the mass. Okay, so right there, this is just going to be the gravitational force. And then there's going to be a buoyant force that's acting up, via the barge, right, kind of the raft, which we'll call FB. Okay, so those are our two forces. One acting down, one coming up. And actually, let's go ahead and make them the same size because this is definitely equilibrium. Because we have a balancing of forces, because otherwise it would be bobbing up and down, for example, if it was in oscillation, or we'd have a case where it was actively sinking. But that's not what's happening here. Instead, we have a case where the only two forces, the gravitational force acting down and the buoyant force pushing back up, are equal and opposite. Okay. All right. So then what we want then in terms of our key equation is just Newton's second law. Okay, so we want F net equals ma. Okay, so that's our system, but it's going to be simplified, or that's our only key equation, because a is 0. Why do we know it's 0? Because otherwise it wouldn't be floating. We wouldn't. This would be, if we just took, say, the crate and just threw it in the water and let it sink, then we could solve for its acceleration. At what rate does it sink? Or if it was a stone or something and we threw it in a lake, at what rate does that stone sink as it sinks to the bottom of the lake? But that's not the question here. So we know that the acceleration is 0. All right, so that does simplify the system. And what's often the case with net force, we're going to write that single term, so F with the subscript net, as a sum of two forces. All right, and we'll stick with the idea that the positive direction is up. So we'll just call this positive y. And so then we're just going to have a case where we have the gravitational force, or rather the buoyant force being the first one, the positive one, and then minus the gravitational force. Those are the net forces. That's the total of all the forces. And we know that that's going to be equal to ma, which is just m times 0, which is just 0. Okay? So now it comes down to the kind of the other key equation here is that we want to identify what the buoyant force looks like. Because we know the form that the gravitational force looks like from previous problems. We know that the gravitational force is going to be mg. And I'll write that down in just a second. But the buoyant force, that's the new kind of force we're looking at in a problem like this, it has a particular look to it. And what it always is it's the density of the water, the volume of the water displaced, and gravity. Okay, so it's got gravity in there because it's tied in with gravity. But what's different about it is that it's related to the fluid that's displaced, and specifically the mass of the fluid that's displaced, which we express as density times volume, because density times volume is mass. Okay, so I'm going to actually show that as an intermediate step with the whole idea of density times volume being mass, because that way you'll really see that this is just two expressions of mass times gravity. So let's go over here. Over here, I'm going to write for the buoyant force, mass of the fluid, so F for fluid, that is the fluid that's being displaced, pushed out of the way by, originally by the barge itself, because the barge has mass, push the water out of the way. And when we put the crate on top of the barge, it pushes even more water out of the way. And that's exactly what we're trying to solve for, the volume at least, because we're trying to find out how much deeper does the barge flow. Well, if we can find the volume, then we can think about the actual, the width and length of the barge, and then the third dimension is going to be the height, and that height is going to be precisely how much deeper the barge sinks because of the crate. And so the total of the three, length times width times height, that's the volume displaced. Okay? So far, though, I just have mass of the fluid displaced times gravity, and then minus the mass of the crate, which again, we're just calling m with no subscript, also times gravity, all right, equals 0. See? All right. So we've got these two cases, and we can actually go ahead and cancel out gravity because we can just divide both sides by g. So if I go and I say, okay, I'm just going to divide everything by g. Well, 0 divided by g is still 0. You can't divide things by 0, but you can certainly divide 0 by things. In this case, by a number that's equal to 9.8 meters per second squared, or approximately 10. And so then you can go ahead and see that we have some nice cancellation here. All our g's cancel out. Okay? Right? And this just remains 0. Okay. So then our system here is going to then simplify to just the mass of the fluid minus m equals 0. Now, I said there's another key equation here, and I didn't lie. I just haven't quite got to it, because the key idea is that mass is density times volume. Okay? So I'll write that down over here. I'll say mass, all right, kind of like, think of this as a definition, is density times volume. Okay? And you can check how the units work out on that one, and it certainly makes sense, right? So the density of something is, how much mass there is per volume. So you multiply that by volume, and you just get mass, right? Okay, so then we'll go ahead and rewrite the mass of the fluid as the density of water times the volume of the water displaced. See where we're going with this? Okay, so then we're just going to kind of continue down here with just rewriting the same net force equation, the same Newton's second law equation that we started with up here, right? F net equals ma, in this case, F net equals 0. So then it just becomes the density of water. So density is usually represented by a Greek letter rho. I write mine like this to differentiate them from p's. So this is the density of water, okay? Then times the volume of the displaced water. So I'll write dsp for displaced, okay? And then that's just going to be minus the mass of the crate equals 0, okay? Because this all came from a balancing of forces. So then we can go ahead and solve directly for the volume displaced with a little bit of algebra. I'm just going to add m to both sides, all right? And then I'll divide both sides by the density of water, which you do need for this problem, all right? So divide both sides by the density of water. So over here, you would just have put over here, the m, right, which will be the only thing on the right-hand side at that point, because you've added to both sides, which will, of course, cancel it out here, right? And I didn't need to use such a thick pen. There we go. And so then on the right-hand side, we just have M divided by rho water. I'll just shorten that to a W to save a little bit of space. All right, and then over here, these are going to cancel out. So then we're just left with the displaced water equaling the mass of the crate divided by the density of water. All right, and then the density of the water, what is that, you ask? Well, it's actually a pretty easy number to remember, but you don't have to memorize it. It's 1,000 kilograms per cubic meter. Okay, and you can see it sometimes expressed as grams per cubic centimeter, which are not numerically equivalent because it's 1 gram per cubic centimeter because of the conversion rate between kilograms to grams and centimeters or cubic centimeters to cubic meters. And there's also obviously non-metric ways of expressing it, but this is the most basic way to do it. This would be the physics view of density. Kilograms per cubic meter. Chemists usually think of it more as grams per cubic centimeter. Regardless, let's go ahead and actually plug in our numbers. Let's find it. All right, and we'll almost be done. And I'll talk about what we do with this volume. Okay, because at this point we'll just go back to the reasoning that if we have a volume and we know two of the three dimensions, then we're literally just solving for the last one. Because again, that's what it asked for. It asked for the height. Okay, and I'll elaborate that in my sketch as well. But let's plug in our value. I was using, I believe, 290 was the number I decided on for the math. So zooming out a bit here. So we'll put in our 290, and we're just going to divide that by 1,000. All right. So in cubic meters, we have a volume displaced of 0.29. All right, cubic meters. So that is the amount of water that's displaced. Okay. So water displaced. All right. So again, we are so close to being done, and I'm going to go ahead and take this value right up top because we can finish off right here near where we'll put our final answer. So we know now that our volume displaced is, as I said, 0.29 cubic meters, and all we need then is to relate that to the 4 meters and the 5 meters, which is the length and the width of the barge, because what we want to solve for is that height, the height that the barge sunk. And we're not solving for the actual height of the barge. We don't know what the original height of the barge was, right? We don't know how thick the barge is essentially, but we're just solving for the difference in where it sits in the water because that's going to relate to the displaced fluid, you see? And so this is the H, right? And so, in 3 dimensions then, if we put everything together, right, that's going to be, this is the volume that we're interested in, the volume of water that was pushed out of the way, displaced. And since we know, 2 of those 3 dimensions, we just need to solve for H. And so as an equation, what this would look like is the volume of a, 3-dimensional rectangular solid, right? Like a book almost, right? Kind of like long and flat and just, but still, having some thickness to it. Well, we have a case where, let's move this out of the way and then undo that. All right, there we go. Just have to fix my mistake there. All right, so we have kind of by definition here that volume in general is going to be length, L for length, W for width, and then H for height, right? So that would be for, a rectangular solid, nothing like a cylinder or sphere, right? So this is kind of an easy formula for volume. And we know everything in this equation except for H. So you can see then we can just plug everything in. We know that the volume is none other than the volume of water displaced. The volume of water pushed out of the way, so 0.29 cubic meters, and then we'll put in our 4 meters times our 5 meters times H and solve for H. And we are done. All right, and so solving for H would just be dividing both sides by 4 times 5, which is 20. So I'm just going to take my 0.29 and divide it by 20. So 0.29 divided by 20 gives me 0.0145. All right, and that is our answer. All right, what would the units be? In meters. All right, and if we wanted in centimeters, it'd be 1.45 centimeters, but in meters, it's 0.0145 meters. All right, nice. All right, so let's quickly look at the second one. This one goes quite a bit faster. All right, so this is just Pascal's principle. That is the idea here. Let me go ahead and write that down. This is Pascal's principle. All right, not to be confused with Archimedes' principle, because there's quite a few principles when you start studying fluids, right? And so sometimes the names get mixed up. By the way, the topic of the first problem was buoyancy, okay, which is that idea of the buoyant force just being equal to the mass of the displaced water times gravity, right? That's the key idea. All right, and we take that mass and we express it as density times volume. But here we got a different type of system. We have a hydraulic system with a piston in and a piston out. Okay, and this is a way to get a mechanical advantage. In other words, to get more force on the output than the input, like essentially like a hydraulic jack that lifts a car that employs this principle. So how much more force can the larger piston exert compared to the force applied to the smaller piston? Okay, and so in this case, we have a couple values. So we're told in the hydraulic piston shown in the sketch, the small piston has a diameter of 1.8 centimeters, and the large piston has a diameter of 5.8 centimeters. Let's mix these up a little bit. Let's go ahead and make this one 1.1 centimeters, and we'll make the diameter on the big one 9.3 centimeters. So a more dramatic difference in size, which will give us a bigger force increase. Okay, so our single key equation here for Pascal's principle for a mechanical system like this is we have that the idea then is that we have that the pressure in equals the pressure out. So that actually comes directly from the work in equals the work out, which is a conservation of energy statement. But here, think of it as being customized to fluids. So we can think of it almost as a conservation of pressure, or like a delivery of pressure, the fact that the pressure doesn't get lost anywhere in the system because the system is all sealed up. There's nowhere else for the pressure to go. All right, so the pressure at any point has to be the same, right, in a system like this. Okay, now obviously the pressure at any point in the ocean isn't the same because there's that effect of what's called hydrostatic pressure. There's a difference in depth, but anytime you talk about Pascal's principle, you're assuming that there's either negligible or no difference in depth, and so that's not part of the consideration. So we simply have the key idea here, the one key equation you need is pressure in equals pressure out. Okay, so P here represents pressure, and pressure by definition is force per area. Okay, so it's force per area, which means force divided by area. And so then we can rewrite pressure in equals pressure out as force in area in, right? So that's like the input piston, the smaller one, okay, equals force out times area out. All right. So then let's think about what we know, right? We know the area out and the area in, and we're asked for just a ratio of large to small, okay? Well, the F out, what I call F out, is exactly F larger, see? Because the larger one is the output. Otherwise, you would get a reduction in force, and you don't want that, right? Unless actually you're trying to maybe do some fine scaled work, and you actually want to reduce your force, but usually you want to increase it. And so then F in, that's F smaller, okay? And you can kind of tell here, right? Because you can see the arrow in, arrow out, right? The arrow in is on the small one, the arrow out is on the big one, okay? So then to rearrange that, we would want to divide both sides by F in, and then multiply both sides by A out, okay? So let's do that as two separate steps, and I'll do it in a slightly different color of red here. So I said I was going to be dividing both sides by F in, okay? So I'll take the idea here that I'm just going to multiply both sides by 1 over F in. And over here, same thing, 1 over F in, because anytime with algebra, as long as you do the same thing to both sides of the equation, it's totally allowed. And you can see then that that's going to cause F in to cancel out on the left-hand side, and then we're going to have a expression that remains 1 over A in, okay, equals, and notice I'm writing my fractions a little bit more carefully here rather than using the slanted, right? I'm using the horizontal line so you can really clearly see what's in the numerator and what's in the denominator. And so we have F out up top, we have A out down below, and I'm sticking with my names so far for in and out. Obviously, I'm going to want to correspond that to smaller and larger, as I did a moment ago when we put the final answer in, or just make that clear. And so then, as our next algebraic step, I'm simply going to multiply both sides by A out, okay? Because that will cancel it out on the right and leave me with just a ratio, which is to say a fraction of forces on the right and a fraction of areas on the left, okay? So over here, I'm just going to multiply by A out and multiply by A out over here. You can see then that has some nice cancellation. The A out cancels completely from the expression over there on the right. And so then when we rewrite this, we're going to have A out over A in equals F out over F in. All right. Well, F larger over F small, that is out over N. All right. So that's none other than large, right? Just well, larger, smaller. We can just call them large and small as well. All right, so you can see that just the same name, right? Or just the same force by a different name. Okay, so then you can see that our answer is just going to be A out over AN. Well, we know those, right? We know that what, those values are because we're given the diameters. So how do you relate diameter to area? Well, that's in itself a key equation, if you will, right? It is the equation for the area of a circle, and the area of a circle is pi r squared, or pi d for diameter over 2, because the radius is half the diameter. R, by the way, is radius, of course, squared, right? And so that's just going to be pi d squared over 4. So the area of a circle is pi d squared over 4. Okay, so then we're just going to have two sets of those. So we're going to have, you can see, right, on this side, on the A out over AN, we're going to have our pi, we'll have our d expression, d out squared, all right, and then divided by 4. And then in the denominator, pi dn squared divided by 4. But since they're both circles, so they're both, pi in diameter and so on, that the pi and the 4s, those all cancel out, right? So we actually only need a ratio of the diameters. So it doesn't actually matter if we're given the diameters of the radii, because we're just going to be interested in their ratios in both cases, okay? So you don't have to worry too much about that. What you do have to worry about, though, is that you're given a value that has a squared relationship to area. So you do have to remember that you're taking a ratio of the squared diameters, not a ratio of just the diameters themselves. Right? It's an easy mistake to make. If, on the other hand, you were given the area of the pistons, then, of course, as you can see, you just take a ratio of the areas. All right, so then we have cancellation of the 4s and the pi's. And so then this then will just be rewritten. And all I'm doing right now is just rewriting everything on the left of the equation. And so this will just become, and you know what? I'm going to switch over to the notation, the larger, smaller notation. That will be all done. So then this is just going to be d, and out is larger, squared, and then d smaller squared, you see, right? And that, of course, as the line above shows, is equal to the larger force over smaller force, just like that, okay? And so the force, the force increase that we get is just going to be the d larger over d smaller. And we can go ahead and plug those in. I'll copy this up over top and bring it up right next to our box. We'll put our final answer after I do the calculations off to the side in Desmos. Okay, so plugging in our value, we have our values, or two values. We have the larger one of 9.3 centimeters. Now, is it important that I convert that over to meters? No, because it could be in inches, right? Which we never use in a physical science class because we want to stick in the metric system. But since it's just a ratio, whatever the units are, they cancel. So it could be just some made up unit as long as it's the same for both. Okay, but so I'll just keep it in centimeters. So we're just going to have 9.3. Again, the important thing is squaring it. And then that divided by 1.1 squared. All right. So then our ratio of the diameters squared is equal to the ratio of the force increase that we get, the mechanical advantage we get. And we can see for my chosen numbers, it is 71.5. Right? Rounded. Because the 7, of course, rounds the 4 up to a 5. So 71.5. No units, because this is the ratio. This just tells me how much more force I get on the output than the input. I push with 1 Newton, right, which is, the metric pushing force, and I would get 71 newtons out, or 71 and a half newtons out, okay? All right, well, I hope this homework help video has been helpful. Thank you so much for watching.